So in the previous class, we were doing equation of state. Let us start. Let us just recapitulate of what we have done so far. So equation of state we did last time, and what we did was we knew that if we have three variables, that is, if we have a function of three variables, PBT, then in this one of the variable can be expressed as function of the other two. That is, I can express temperature as function of pressure, volume, and so on and so forth. And from this particular thing, we wrote that volume is a function of both pressure and temperature. And from here, we knew that differential change in volume, I can write del V upon del P at a constant temperature times dP plus del V upon del T at constant, del V upon del T at a constant pressure times dt. And similarly, I can write what would be dP. dP would be del V upon del P upon del V at a constant temperature dV plus del P upon del T at a constant volume dt. And from here, I substituted instead of dV, instead of dP, I substituted this, and from which I got a very important equation, which is equals to 1 minus del V upon del P at a constant temperature times del P upon del V at a constant temperature times dV minus del V upon del T at a constant pressure plus del V upon del P at a constant temperature, and then del P upon, I think, del T at constant volume times, I think it was dP, dt, I think, sorry, dt is equals to 0. Now, if I'm considering there are two states which are at the same temperature, it implies that dt must be equal to what? 0. And if dt is equal to 0, it implies del V by del P at a constant temperature is equals to 1 upon del P upon del V at a constant temperature. So what equation of state gives us? It gives us a mathematical relation which can allow us to replace a partial derivative by a reciprocal of inverted partial derivative of the same variables. Okay, so this is very important. One must remember this. Okay, one must remember this. And secondly, if I take what if I take a dv non-zero, and what if I take dv equals to 0 and dt non-zero? So if I take dv 0 and dt non-zero, then certainly I can write that this part is 0, and where is that? Sorry, this part is 0. This part is 0 means it implies that del V upon del T at a constant pressure is equal to minus of what was that? Del V upon del P at a constant temperature and del P upon del T at a constant volume. Okay, and this portion I can write it as simply 1 upon del T upon del V at a constant pressure. So this gives me what? This gives me very simple del V upon del P at a constant temperature. Then you have del P upon del T at a constant volume. And then you have this del T upon del V at a constant pressure is equals to -1. This is an important relation. You should always remember this. In fact, this is not physics. This is generally mathematics. Okay. So from mathematics itself, you can do it. I mean, if you are good at partial derivatives, then in general also you can write this. Not a problem at all. Okay, so I'll write it for you so that you should remember. Um, just give me a minute. Okay. So what I wanted to explain was this. Okay. Now, on that particular day itself, in the last class when we were discussing, I had already defined three quantities. I think one was alpha, and I think if I'm not wrong, actually I derived all these quantities. Already I have explained all these quantities. I hope you remember this. I'm just going to write it so that you remember what I wrote. So I think alpha I wrote as a coefficient of thermal expansion. Coefficient of thermal expansion given by 1 upon V del V by del T at a constant pressure. And beta, I can write simply as 1 upon P del P by del T at a constant volume. And this is sometimes referred to as the coefficient of thermal tension. So this is coefficient of thermal tension. And then you can also define something called as compressibility. Okay, isothermal compressibility. I think that is referred to as kappa T. And that is equals to minus 1 upon V del V upon del P at a constant temperature. So using this, using this one, this is alpha, this is beta, and this is kappa T. What I can do, I can simply write my, if I want to write beta into KT, beta into KT is, if I'm not wrong, it is equals to what? So what I'll do this for you. It will be simple. Um, I think I have made some mistake while writing. Just give me a minute, I think. Beta is fine. Uh, del V upon del T. Okay, so this is not beta. I think I should write alpha better. So alpha, okay. So what I can do, del P upon del P at a constant pressure. I know this. Okay. So what I can do, mm, if I just do alpha upon KT, what I'll get? I'll just get something like del V upon del T at a constant pressure. And then I have this del V upon, so sorry. If I divide this alpha upon KT, so this is my, let's say I give it an equation number 1, I give it an equation number 2, and I give it an equation number 3. So if I divide 1 by 3, what I'll get? Alpha upon KT, there would be a negative sign as well. So negative sign minus del V upon del P at a constant temperature. Okay, I'm so sorry. Okay. Um, So what I have got alpha upon kt is equals to minus of del v upon del t upon p and del v upon del p at a constant temperature. So I'll write del v upon, here I'm writing this. Please see it here. Del v upon del p at a constant temperature 1 upon, 1 upon del v upon del t at a constant temperature. I can write this as, so del v upon del v at a constant temperature 1 upon. So I'll take this here. It will be minus of del t upon del v at a constant pressure into del p upon del t at a constant volume. So I can replace this here. And if I replace this here, I'll get alpha upon kt is equal to minus of del v upon del t at a constant pressure into del t upon del v at a constant pressure into del p upon del t at a constant volume. So this cancels out because, how should I explain? By the reciprocal results, it is 1 upon del t upon del v at a constant temperature, at a constant del t upon del v at a constant pressure would be 1 upon del t upon del v at a constant pressure will be equals to del v upon del t at a constant pressure, from the reciprocal relations that we can obtain from the equation of state. Okay, so from here it is clear that I can also write this thing, that is alpha upon kt is equals to del p upon del t at constant volume. So del p upon del t at a constant volume is nothing but it is equal to p times beta. So what you've got pressure into beta into kappa t is equals to alpha. I hope it is clear. Okay, so this is the remarkable relation that we have already developed. Okay, so this is, I think, something that you should remember because this is an important thing that you should keep in mind. Okay, so basically, I should write it here itself. How we define things? We define one of the quantities which is called as 1 upon v del v upon del t at a constant pressure. Okay, this is something that we had defined. Uh, uh, it is called as a coefficient of thermal expansion. It is called as a coefficient of thermal expansion. And we denote it with alpha. I think some other books may have some other things, but I have denoted by alpha, or simply I can write it as expansivity. Okay, so just think about it. So what would be expansivity for an ideal gas? So for example, if I take ideal gas, then PV is equal to nRT. So volume becomes equal to what? nRT upon P. So if I differentiate del V upon del T, then what I'll get? I'll simply get nR upon P. So instead here I can place nR upon P. So alpha becomes what? nR upon PV. And I know what is nRT. nRT is equals to what? PV. So if I just replace T here, this nRT upon PV becomes 1. So basically for ideal gas, my expansivity is reciprocal of the temperature. Okay, so my expansivity depends upon the temperature. So for ideal gas, you can write my expansivity. For ideal gas, expansivity depends on temperature. And what are the somebody can ask you what are the dimensions? The dimensions of or units of expansivity are k raised to power minus 1. I hope it is clear to you. Similarly, another term that we studied was what? Another term that we studied was what? Uh, I can say that it was compressibility. Okay, so there are two terms. One is called as a compressibility. Another one is called as the expansivity. Okay, so expansivity, I'm writing it as 1 upon V del V upon del T at a constant pressure. So what I can write, I can also write that my expansivity is nothing but 1 upon V. I can write my dV at a constant pressure divided by dt at a constant pressure. So I can also write dV at a constant pressure divided by V divided by dTp. So how can I define expansivity? Expansivity can be written as the limiting value of what is dVp upon dV? Fractional change in volume. Limiting value of fractional change in or fractional increase in volume, you can say, rather, if I'm taking it as positive, fractional increase in volume per unit what? Per unit temperature change at a constant pressure. Per unit temperature change at a constant pressure. At a constant pressure. Is that fine to you? So this is how you can also define your expansivity. So I hope this is just for as a matter of recapitulation. I'm teaching you all these things. All these things we have done in the previous class itself. Okay, then what is isothermal compressibility defined by kappa T? If you remember, I've already told you why it is negative. Why negative sign is here? So it is minus 1 upon V del V upon del P at a constant temperature. This is called as a coefficient of isothermal compressibility because isothermal means temperature is constant. Okay, so this is basically what why negative sign is there, because I know that whenever volume decrease, pressure increases. So corresponding to the decrease in volume, you have an increase in the temperature and increase in the pressure. So basically del V upon del P inherently is always negative. Inherently is negative. So we apply a negative sign so that we get this coefficient as positive. Okay, now what for an ideal gas? For an ideal gas, I can write minus 1 upon V. V can be written as nRT upon P. So if I write nRT upon P, derivative and minus nRT upon P square. So if I write V is equal to what? nRT upon P, then I can write del V upon del P simply as minus nRT upon P square. I can replace this here, and what I'll get? I'll simply get kappa T is equals to nRT upon E is pressure, so 1 upon pressure. So the units will be inverse of that of pressure. So basically the units will be of the order of 1, or I can write meter square Newton inverse. Okay, this is how the units of the isothermal compressibility would be. So I hope this is quite clear to you. I don't think there is any problem with this. And now if I want to write fractional change in volume and things like that, then what I can do, I can also write all these things in terms of my compressibility and all those things. So if I want to write what is the fractional change in volume, so fractional change in volume is del V upon del P at a constant temperature dt plus, I can write plus del V upon del T at a constant pressure. I'm so sorry, it is dP at constant pressure dt. If I'm not wrong, okay. Now remember, what is del V upon del T at a constant pressure? So just remember, del V upon del T at a constant pressure is nothing but alpha. Okay, so if I just divide it by differential dV, so this will give me 1 upon P dV upon delta V upon delta T at a constant pressure dt plus del V upon del P times dP and then 1 upon V. So clearly this is equal to what? Alpha. So I can write it as alpha dt minus this is what? Isothermal compressibility kappa T dP. So this is also how you can write fractional change in the volume. You can express it in terms of expansivity and isothermal compressibility. Okay, so if I'm writing it here, if uh, we know alpha and kappa t experimentally, if I can know these values experimentally, and they are known as function of what you can say, function of temperature and pressure, temperature and pressure. Okay, then one can find the equation of state by integrating this. Now we can integrate this and find the equation of state. Okay, so for example, if somebody finds out, let's say if somebody finds out that my expansivity happens to be a function of temperature, and let's say it's very simple 1 upon T, and let's say somebody finds out that my kappa T is a function of pressure and it's just simply 1 upon P, then one can clearly see that equation of state will be given by dV upon P 1 upon T dt. 1 upon T dt and minus 1 upon P dP. And this is how we can integrate. We'll get log of V is equals to log of T minus log of P. So from here it is quite evident that gives me PV upon T is equals to constant, which is again an kind of ideal gas equation only. So I can obtain an ideal gas equation. This is what I've told you, that for an ideal gas we know that alpha T is somewhere related as 1 upon T, and kappa T is as a function of pressure can be written as reciprocal of pressure. So clearly one can find this way. Is that fine? I think this is quite evident. Okay. For example, in general, I'm just writing all these things in general because I don't know what comes in your exam. So I'm just giving you all these things. So let's say I've already written this as alpha dt minus kappa t. I think this was dp if I'm not wrong. Okay. If I get this thing, so let's say if I want to have initial conditions, let's say initial conditions given to me is P naught, V naught, T naught, and any arbitrary state is Vp and T, then I can integrate from V naught to V. I will simply get V minus V naught is equal to alpha uh, uh, alpha dt integral from V naught to V, and in fact this is T now, so I can write it as from T naught to T. Okay, and minus kappa T from dp from P naught to P. Okay, and then there would be a volume also here, volume term also, because this dV will go there. Okay, so if I consider a solid, generally for solid, the volume change during this during expansion and all those things, and during compressive, when we compress a solid, the volume change is very less. And since this is very less, I can assume that that volume remains constant. And for solid, if I take volume to be almost constant, then how will my volume? So how can I can write my V minus V naught is equals to this alpha comes out, B comes out, this becomes T minus T naught minus kappa T volume, and then this becomes P minus P naught. Under such very crude approximation, what approximation I have taken, to the first order approximation I can take that volume change of a solid is relatively small when pressure and temperature are changed. When pressure and temperature are changed. So basically, if I write this thing, if I think this way, that volume change remains very less. This is kind of approximation I'm taking. If I take this kind of approximation that during the change of pressure and temperature, in case of solids, the volume change V is very less. So I can assume volume to be a constant, and I can take this out of integral, and I'll get that. I can write that my volume V can be expressed as V naught 1 plus B T minus T naught minus kappa T I think this is P minus P naught, P minus. Okay, so if I here I have taken beta and kappa T to be constants only. So if I've taken them constants, they will come out. So basically what I can do, if I know the measurements of expansivity and compressibility, and if I have the knowledge of the initial reference state, that is P naught, V naught, T naught, then we can find the equation of state of the solid. Obviously here subjected to these approximations. Okay, obviously I've subjected them to these approximation as I've mentioned. Okay, so I hope this sums up your equation of state. And okay, so this sums up your equation of state. So basically this is how I can, this is what I can make justice with equation of state. Now let us move to an important topic, which is the first law. And before moving to the first law, let us do something regards work and heat. What is heat and what is work, and so on and so forth. Okay, so let us first discuss the concept of heat. So before moving to the first law of thermodynamics, which I'll introduce later on in the class today itself. So let us discuss what is heat. So heat is a form of energy transferred between two or more systems and its surroundings by a virtue of the temperature difference. So basically, what is a physical quantity that should be different? It should be temperature that should be different. Okay, so heat is nothing but it is energy in transit. Energy in transit, and this energy transits when there is a temperature. So basically, when there is a system at a higher temperature than the other one which is at the lower temperature. Generally, what we say low temperature body, we call it as a sink, and the high temperature body, we call it as a source. Okay, so heat is an energy heat is a sort of energy in transit, or we can say heat is the energy that flows between a system and its surroundings because of the temperature difference. Okay, so this is quite evident. This we know from our standard kind of experience also, that if the system Ts is here and surrounding temperature, I can write it as Te. If Ts is less than Te, that is environment temperature is greater than the surrounding temperature. Okay, so what will happen? Energy flow will take place in this direction. Okay, if the source temperature is greater than the surrounding temperature, then my heat will flow in this direction. Okay, whenever energy flows out of the system, we take by convention negative, and whenever energy flows into the system, we take it as positive. Okay, so this is a kind of notations that I'm writing. Always remember that heat is a directional quantity. Okay, so heat is a directional quantity. Whenever we are transferring a heat to the system, we take it as a positive. Whenever heat is taken away from the system, we take it negative. So whenever I say that the temperature of the system is greater than the temperature of the environment, so basically what will happen? Heat will flow out of the system. Okay, remember that heat and internal energy are two different things. We'll come to internal energy later on, but right now just remember heat and internal energy are two different things. Okay, basically you remember in your standard 12 there was a quantity called as work. So work basically in physics, how does work? We take work you know from work energy theorem that work is equals to the change in the kinetic energy of the system. It is equals to the negative of change in the potential energy of the system. Okay, work done by an external force, is equals to the net change in the potential energy. So basically, how we use it as a transaction. Understand the energy. We use the work as a transaction to understand the energy. Okay, so basically, similarly, heat also is like work only here. Okay, it represents what you can say a way to understand energy, or represents a way of transferring energy. Okay, understand that neither heat nor work, neither work nor heat are intrinsic properties. That is, nobody would say that this amount of heat is contained in the system. Okay, nobody can say this amount of heat is contained in the system. Okay, and we have to understand another property. So we have to remember that heat and work, okay, unlike pressure, volume, temperature, they are not state functions. They are not state functions. Okay, so this is something that we have to understand. Now the point comes out. Uh, comes out. That point comes out is what is work, and what is work, and all those things, and how to write an expression of work. Because if we are going to go further, then we are going to see how to write different expressions for work. Okay. Okay. In thermodynamics, let us say we take an example of piston only. Okay, so we take an example of gas filled, and gas is filled inside a container, and there is a piston supplied, put here. So basically, this gas would do a certain work. Gas would do a certain work by the virtue of its pressure. Okay. So basically, if a system as a whole exerts a force on its surroundings, so basically this was your system, if you remember, I told you, and this was my surrounding. Piston was there in my surroundings only. So if a system as a whole exerts a force on the surroundings so that a displacement takes place, we say that work is done. And in thermodynamics, we mostly have to do something with external work. So some external work is done. Okay. So if gas is contained in the cylinder at, let's say, some pressure, constant pressure or uniform pressure, and it expands, then it imparts some kind of force to the piston and does some external work on its surroundings. Okay, so in general, in thermodynamics, we are going to talk of something called as external work. Very simple. Work done by the system is positive. By the system is positive, and work done on the system is negative. On the system is negative. This is something you should remember. Okay. So in whatever discussions we are going to do, we are going to do this way only. Whenever we are going to talk of work done by the system, because if the work done by the system, then let's say in this particular scenario, if work is done by the system on the piston, so what will happen? Obviously, so basically system would expand. System expands against what? Against pressure. Against pressure. And in this expansion, what happens? Your dV becomes positive. we say that work is positive. That is, work is done by the system. And when work is done on the system, what will happen if I do work on the system? That is, if I push, so basically piston is going to piston is going to push it. So basically system is going to get compressed. In that case, dV becomes negative. And we say that work is negative. So work is done on the system, then always remember we take W to be negative. And if work is done by the system, then we take W greater than 0. So basically, these are the sign conventions. And in different other fields, people take different other things. But in physics, we are going to take this. Okay, so engineers behave a certain different way. But right now, we are going to take these. So I'm not going to change these notations anyhow in our uh, future discussions. Now, let us develop some expressions for work. Expressions for work. So if I want to express what is work, so work is written as work done by the system. I will write delta W. Why I'm using this kind of notation? I'm using this kind of notation since I have to understand that work is not a state function. Lately, I'll make you clear why it is so. Just understand this notation stand this way because work is not a state function. I'll let you know what it is, but right now just write it. Work is not a state function. Since work is not a state function, I'm not going to use a differential D here. I'm going to use this kind of demo. Is that fine? So let's say I'll use a simple way of looking at it, how to understand this. So basically, I have a piston here of a cross-sectional area, let's say A. I have a piston here of a cross-sectional area A. Cross-sectional area is A here. And what happens because of the gas, because of the force of the gas, let's say it expands. So now let's say it expands and let's say it covers the length of dx. It covers the length of dx. So what is dv? dv will become adx. adx. And what is work? Work is nothing but force into displacement. And what would be force? Force is pressure is equal to what? Force per unit area. So I can write this P into ADX. So del W becomes P ADX. And what is ADX? ADX is the delta V. This is dV, differential volume. So basically, work done by the system can be expressed as PdV. Always remember this. Okay, so whenever we talk of work done, although I introduced all these things because I know this is something that you know from your standard 12. So work done by the gaseous system on its surroundings uh, is given by integration from V initial to V final. Now I can write it as P dV. I hope it is clear. Now there can be different cases for which uh, we can find different expressions of work. We can find the expression for work. So let us find expression for work for isothermal process. Let us find the work for isothermal process. So if I'm talking of isothermal process, the gas would expand or contract at a constant temperature. So if it is the case, then pressure P into V becomes constant. And if P into V becomes constant, I know this will be it. So this is how my indicator diagram would look like. And let us say this is my initial position. Let's say I get to this position. Then what will be the work done? Work done will be given by the area under this curve. So area under this curve, so P, V, VI to VF. And I can simply write P dV. And what is P? So P is nothing but it is equals to nRT upon volume. If I take an ideal gas, then I can write P as nRT upon V. And if I replace this, I will simply get nRT ln of V final upon V initial. So this is the work done in isothermal process. nRT ln of V final upon V initial. If I'm talking of expansion, then Vf will be greater than Vi, and in that particular scenario, the work will be done by the system. Okay, and if I'm talking of V is less than Vf, then work done by the system will be negative, clearly, because we know that log becomes a negative whenever you have quantities between 0 and 1. So for x between 0 and 1, your log becomes negative, and your log becomes negative, then the work done by the system, work is done, then this particular scenario would be negative. This particular delta Wt would be negative, implies work is done on the system. Okay, work is done on the system. I hope it is clear. Now let us think of isochoric process. All these things you have studied and just writing it for the sake of doing it, so that you should remember that whatever you have done in your standard 12. And my main target will start tomorrow, where I will derive an expression for work done. Probably if time allows, I'll do it today itself. Okay. But overall, this is an important topic. So you have to really take care of this topic. So in isochoric process, what pressure becomes constant, and if a pressure becomes constant, what will be work done? If you remember slightly, that if pressure becomes constant, then I can write P dV integration from V initial to V final. This will give me P V final minus V initial. Simple. Okay. Isobaric, sir. Isobaric. Okay. In isochoric process, what happens? Volume remains constant. And if volume remains constant, then dV would be what? Equals to 0. So work done would be equals to 0. Since volume remains constant, so work done would be 0. Okay. And you have to remember one very important thing. It is not necessary that that only volume remains the same at initial and final points. It should be constant throughout. Okay, so I'm just writing, it is not sufficient. It is not sufficient that process starts and ends with same volume. Starts and ends with same volume. Rather, it must remain constant throughout. It must remain constant throughout. Okay. Only then your work would vanish. Only then I can write that in isochoric condition, my work would vanish. Okay. Now, what happens if I'm talking of adiabatic conditions? What if I talk of adiabatic conditions? So let me talk of something like adiabatic conditions. So from your okay, there it is. Adiabatic conditions. So if I talk of adiabatic conditions, now if I remove my gaseous system from any thermal contact, okay, and if I put it on rest on an insulating slab, then there will be no such heat exchange. Okay, and now if we do work on it, the temperature will change. Now if I do work on it, the temperature would change. So basically, if I am doing a process by removing a thermal contact, by putting it in a thermal insulation, that is, if I'm not allowing heat to be exchanged, I'm talking of adiabatic condition. And now if I work on the system, the temperature will change. Such conditions are called as the adiabatic condition, or such process which is carried out in thermal insulation is called as the adiabatic process. The equation of state is given by PV raised to power gamma is equals to constant, and here gamma is nothing but it is Cp upon Cv. This is a dimensionless parameter. Cp is specific heat capacity at a constant pressure. This is specific heat capacity at a constant volume. Okay, so this is a dimensionless parameter, and quite often gamma is greater than 1 only. So gamma is greater than 1, which implies that if I want to find the slope, so its slope will be much steeper than the slope of PV. And PV is equals to constant is the equation of isothermal process. So you have to remember, if I'm making an indicator diagram of isothermal process, and if I'm making an indicator diagram of adiabatic process, then the indicator diagram of adiabatic process will be steeper because of gamma being greater than 1. Okay, so from here I can write that work done by the gas in expanding, because it is much steeper now, so it is much steeper. So work done by the gas in expanding adiabatically from Vi to Vf is smaller than work done by the gas in expanding isothermally. Because you have to remember, how would you write the expression of work? Expression of work will be written by PdV. And if I'm writing PdV, so instead of P, I will have to write what? Some constant times division by volume. Now, if I do it in adiabatic condition, this is PV raised to power gamma. Gamma is obviously greater than 1. So work done by this gas in expanding adiabatically will be lesser than the work done by the gas in expanding in under isothermal condition. That you have to remember. So now let us derive this thing, the expression for work in adiabatic condition. So this will be given by delta W from V initial to V final is equals to P dV, and this will be some constant. I'm not going to write that. I'm just writing it as PV raised to power gamma. So this is V raised to power minus gamma. What should I do? I should write something, no? So let me write, instead of writing it as, so let the initial coordinates, initial points V, Vi, and Pi. Now, in general, at any later instant, PV raised to power gamma, the general P and V would be equals to what? Py Vi raised to power gamma. Okay, so I'll replace it here. It will be V initial to V final. What is P? P I can write simply as Pi Vi gamma upon what is P? Simply divided by V raised to power gamma. Remember, this is constant, so these things will go out of the bracket. Integral, that is Pi Vi raised to power gamma, integration from Vi to Vf, V raised to power minus gamma dV, and this will give me Pi Vi upon gamma minus 1 Vi 1 minus gamma minus Vf 1 minus gamma. Okay, and then we can have all sort of different things you can do from here itself. what you can do. You can also take some VI raised to power. Sorry, I think I have forgotten this. You can take this common out, so I'll get PI VI upon gamma minus 1. This will be 1 minus VF upon VI raised to power 1 minus gamma. So all these things can be done at your end, and you can always play around with some parameters. Things like this can be done. Now, in the next lecture, we are going to start with the thermodynamics of the behavior of the paramagnetic systems. Okay, at extremely low temperatures, and we are going to derive the expression for work. Okay, so till now we have done the systems which are concerned with the gaseous state, and now we are going to do the we are going to find the work done by the work done in the cases of the expression for the work done in the cases of paramagnetic systems. So this we are going to do in the next lesson. And the next class itself, we are going to derive, we are going to find that whether work is a state function or not a state function, and why we are using this kind of notation here. Okay. So till then, take care. Bye-bye.